John will talk about the surveillance from a nanoscience perspective and how we can how we can detect, let's say, the counterfeit of different types.
Thank you very much, Anne-Marie. Before I start, I would like to make everybody aware that a copy or copies of my handwriting will be available after the session, and I can assure you that the price will increase even more than what Dr. Suwan said. It's a pleasure to be here today to give you this presentation. We started working in nanoscience about 10 years ago, and it began as a fairly small scale in our laboratory, and it has flourished to be in the principal area of research in the lab. The presentation today will concentrate on the application of nanoscience, nanotechnology in security. I will take examples from the literature and some from the work which is being done in the laboratory presently. First of all, let me just start by a simple definition of security: the protection or defense against attack, interference, espionage. The state of being or feeling secure, freedom from fear, anxiety, danger, doubt, state of sense of safety or uncertainty. A concern for security has historically ranged from national defense to peace and tranquility in our streets and issues of law and order. In more recent times, a concern from security has taken renewed meaning to stand as protection from unprovoked attacks on innocent people traveling, working, or simply enjoying the fruits of their labor, to all sorts of terror acts ranging from poisoning water supply to the destruction of historic monuments. The security challenges which we face, as you can see on this overhead or on the slide, are chemical and biological agents, border security, critical infrastructure, pharmaceutical and medicine, aircraft parts, for example, and wine and spirits. Now, just to give you some examples of how we're affected by this proliferation of chemical and biological agents, the security agencies have identified 23 bacteria, 43 viruses, and 14 toxins. The border security would involve passport security and the authentication of documents. The critical infrastructure protection would mean the decontamination, for example, of vital utilities such as water supply. That is, if there is an attack, a terrorist attack, and the water supply is contaminated, you have to have a way of decontaminating. The health aspects, we have, for example, that the World Health Organization claims that 10% of global medicines are counterfeit. And from the picture there, I don't really think that one can discern as to which one is the counterfeit and which one is the real one. The security in the industrial supply chain, the example which I have is the aircraft part, and I'll just state an example that the FAA estimates that 2% of aircraft part changes are counterfeit. And in 1989, a tail section of a Corvair 580 tore off at 22,000 feet. The 55 passengers aboard all died. This was over the North Sea. And after the investigation was carried out, it was found that in the tail section there were counterfeit bolts, and therefore it was not meeting the specifications set out by the FAA. We also have counterfeit auto parts, for example, brakes made from sawdust, non-shatterproof windshield, counterfeit toys containing lead-based paint, counterfeit toothpaste containing antifreeze, counterfeit shampoo containing bacteria, and harmful wine and spirits. And I think that to me is the most important, the dangerous wine and spirits. Next, we see the security challenges. The economic security. Interpol estimates that 5 to 7% of world trade involves counterfeit. The revenue loss to counterfeit estimated at €600 billion a year. The European community lost €65 billion. This is equivalent to a loss of 200,000 jobs. a total value of counterfeit Canadian banknote has doubled from 2007 to 2008. The broader economic-wide effects from counterfeiting are loss of employment, loss of tax revenue, higher government spending on health services and crime prevention, and just as an example, the G20 economies spend approximately 20 billion euro annum in increased costs due to crime, and 100 million euro per annum for additional health services. So what we need are enhancement of the capabilities which are available to us. That is, we need to have more authentication, detection, identification, neutralization, and decontamination, and delivery of, for example, antidote. The authentication, anti-counterfeiting prevent crime by reducing the thefts of goods, property, and identity, such as your passport or documents, the detection of chemicals, biological agents, the identification of what chemicals or biological agents are out there, the neutralization and decontamination of the environment, civilian infrastructure, and vital utilities such as water supply, and the delivery methods of antidote using nanoparticles as delivery agent improves the stability, it is a targeted delivery, and increases drug carrying capacity and release the range of the drugs. As a result, security has become a growth industry in almost all the countries in the world as it touches the daily lives of ordinary people everywhere. Amidst all these challenges, a concern for security in our scientific and technical world has led to all sorts of exciting paths for research. And one of the paths of research, which is what we're following, is nanoscience or nanotechnology. So I'll just give you two simple definitions of nanoscience and nanotechnology. As you can see on the screen, nanoscience is the study of phenomena and manipulation of materials at the atomic, molecular, and macromolecular scales where properties differ significantly from those at a larger scale. And then we have nanotechnology, which is really the design, characterization, production, and application of the structure, devices, and system controlling the shape and size at the nanometer scale. Now let me just define for you what is nano. It comes from the Greek word meaning dwarf. A nanometer is 1/1,000,000th of a meter, the length of 10 hydrogen atoms strung together, or about 100,000 the width of a hair. And also here you will see some of the sizes of things. For example, we have the size of the DNA, we have the size of the red blood cell, which is 10 to the minus 5 meters. This is just to show you that we're working at a level which, although some of my colleagues in the field do not approve of saying, but at a very small level. Why nano? Well, because relative size matters. And this is a quote from Professor Ozen at the University of Toronto. The working of the properties in the bulk derive from the fact that bulk materials are much larger than the characteristic length of those properties. Nanoscience happened when this is not true. What does this mean? It means that you have the characteristic properties which change when you go down to at the nanoscale. That is, there is a definite size effect. That is, there are changes in the optical, electrical, and the magnetic properties. And yes, things do change. And this is what this slide is showing you, is that we have at the top, we have both bulk silver and bulk gold, which is what we normally associate also the color of gold and silver. And what we see are the different dots on there which represent the different size of gold and silver, and as you can see, they show different color. That is, they show different properties, and one of them being the color. The other very interesting property, let me just go back. And as you can see also is that the colors were used by artisans in the 16th century to do the color of the stained glass windows. They were using unknowingly nanoparticles by putting into the glass both silver and gold, so they would get this range of colors. Another way of Seeing the properties is through the quantum dots, which are inorganic structure which absorb light and emit in nanoseconds later at a different colors. And you can see on here the quantum dots, again, different size, which is showing you different colors. That is, again, the property changes, the color changes as you go down in size, or in this case, as you increase in size, from 2.3 nanometers up to 5.5 nanometers. Another important property at the nanoscale is the surface area. And Benjamin Franklin in 1773, he did a very simple experiment, which was that he took a teaspoonful of oil, and at Clampton Commons in England, he put this teaspoonful of oil onto a pond, and he noticed that it spread out over the pond. He had approximately 2 centimeters cube of oil, and he estimated that he had covered an area of about 2,000 meters square. And the calculation which can be done shows that you have a 1 nanometer monolayer of oil on top of the pond. Now, this is, again, a very important property which you have at the nanoscale. That is this increase in the relative surface area, which becomes important, for example, in drug delivery. Now, let's look at some of the things which we can do at the nanoscale from the point of view of the security. The nanobarcodes. On top, you'll see the barcodes which are presently used. Another type of barcode which one can imagine at the nanoscale, is by taking silver and gold at the nanoscale and being able to put a code, for example, in this case of silver, gold, and silver, and then being able to detect this pattern by simply using optical spectroscopy. Now, so you can imagine having a barcode such as what is being used today, or a barcode such as the one which is shown at the bottom here. Now, you can have different combinations of silver and gold. For example, in this case, where you've got the 2 metals and you've got 5 places to put them, you can have 32 different barcodes. So you can see how you can go up in the barcodes and multiply the number of barcodes by simply changing the number of, for example, you can use silver, gold, and platinum, or you can increase also the number of spots which you have in order to place the different gold or silver or platinum. The other one is based on the nanomagnets. You have, for example, porous silica, and you can create a random pattern of nanomagnets in the pores. That is by simply placing randomly in the porous silica magnetic nickel, and this will give you a unique magnetic signature which can be used as a code to look at whether the product that you're buying is counterfeit or not. What we're doing in our lab is taking another approach to this. This is the upconversion, what is known as upconversion of lanthanide ions. That is, we make the nanoparticles, we dope them with these lanthanide ions, and then we excite the lanthanide ions using infrared light, and what we obtain is the emission in the visible. The nanoparticles therefore emit in the visible upon irradiation with near infrared light. So therefore you're going from light which your eyes cannot see to, again, something indivisible. This is what is known as a 2-photon process, which I won't get into, but I just would like to mention that. So you can imagine making distinct optical codes. That is, by combining the different lanthanides which give you different colors, right? Then you can imagine, for example, making barcodes such as what I'm showing on the slide. And by looking at the optical spectrum, you can have the different ratios, and that will give you a distinct code. So you can, again, imagine producing codes based on the optical properties, based on the ratios between the different lanthanides which are being used, in order to have a code which, in order to tag certain materials. Now, we also look at, for example, the production of white light, which is, again, very important. And what we're seeing here is, again, the range of colors which one can have, and using these colors to your benefit of making the codes. And this is just to show you that we have that you can get the different colors, for example, by using erbium and thulium. And again, the spectrum here will give you an indication as to what is present in that sample. We also have blue upconversion, and these are two materials which we synthesize in the lab. And again, this is to show, again, the different ions which can be used, the different materials which can be used, the different shapes which you can get. One of them is a diamond shape, and the other one is more of a roundish shape nanoparticle. And again, these nanoparticles here not only can be used in security, but also, for example, the one which is emitting in the blue can be used in photodynamic therapy in the treatment of cancer. And this is the next part which I'm going to deal with, which is how we can use these nanoparticles, not just in security, but also what I would say security of mind or peace of mind. That is, take these nanoparticles and be able to use them in diagnostics, imaging, and, for example, the treatment of cancer. On here we see a nanoparticle, the one which I showed before, which has been coated with silica, and the reason for that is that we can functionalize these particles in order to direct them towards, for example, if we want to image cancer, for example, if we want to image cancer cells. Now, we can also look at the fluorescent staining of E. coli with the lanthanides. What you're seeing here is the E. coli, which has receptors on it for carbohydrate residues such as D-mannose. So therefore, if you're trying to detect in food, for example, the E. coli, you can use the nanoparticles which emit light. So you can detect it via the emission of light, and have specifically the mannose which will go towards the E. coli, and you have the functionalization. And the cellular targeting and uptake, as I mentioned before, this is in the case of the recognition of cancer cells. Cells will attempt to uptake the nanoparticles via endocytosis, as we show on here. The nanoparticle has a specific ligand on it to recognize the cancer cells. That is, because cancer cells have certain receptors on them, the nanoparticle is taken into the cell, and this is what we're showing on the side, which is the cancer cells before and after that we have added the nanoparticles. You can see where you can image those cells, and you also know where it's going into the cell, where the nanoparticles are going. So therefore, the imaging can be done, and you can also have these nanoparticles with a photodynamic dye. That is, they can be excited using the UV, as I showed before, whereby they excite the PDT dye, and this PDT dye will produce single oxygen, which will cause the necrosis of the cancer cells. So I'll leave you with that nanotechnology can act as an enabler in assisting agencies and enhance capabilities supporting security mission for maintaining peace and harmony in society. So therefore, we're going from 10 to the minus 9, which is at the nanoscale, to 10 to the 9, which is the billions of dollars which are being used which are being lost in the economy. And the picture which we see on there is security and how nanoparticles can be used in the national security, the economic security, the transport security, food security, and the health side. And I would just like to acknowledge the present and past people that worked with me on these projects, the funding agencies, and finally, 3 covers from some of the work that we have published, which have been featured on 3 scientific journals, and this is Art and Science. Thank you very much.